Hello, I'm Evan Ariel. This is my Physics 2212 Lab 3 presentation. The purpose of this lab was to use the loop rule in steady-state circuits to examine the behavior of various circuits. We use Ohm's law and Kirchhoff's loop rule mainly, and we observed the behavior of various circuits using ohmic resistors and capacitors. Our results are that using the voltage and amperage measured, we could successfully calculate the resistance of each resistor. It closely matched the labeled value. Additionally, our charge and discharge times for our capacitors are roughly equal for the respective capacitor. Ohm's law relates the change in voltage across a resistor to the current flowing through it and the resistance of the resistor. This law allows for the use of Kirchhoff's loop rule in any closed circuit. It can also be rearranged to solve for the current I or the resistance R. Kirchhoff's loop rule states that the total of all potential differences across any closed loop is zero. This allows for various attributes of each component on the circuit loop to be solved for using known quantities from other components. The system in this experiment was the real circuit components and the closed loops. Surroundings were nothing significant. The components used in these circuits were two 1.5 volt batteries, a 100 ohm resistor, a 47 ohm resistor, a multimeter, a 1 Faraday capacitor, two light bulbs of varying resistance, and wires. In the first circuit, we measured the currents and potential differences across components and used these metrics to calculate the resistance across each component. For the second circuit, we measured the charge and discharge times for a 1 Faraday capacitor by timing the activation of a light bulb. So the resistance across components from part 1 were that the 47 ohm resistor had a measured resistance of 46.7 ohms, the 100 ohm resistor had one of 97.87 ohms, the wires had a measured resistance of 1.5 ohms, and the ammeter had a measured resistance of 0.714 ohms. The charge and discharge times for the two light bulbs are shown below. We have 10 seconds and 12 seconds, and then 55 seconds and 52 seconds. Some possible sources of error are inaccurate measurements, response time, and rounding. What if you charge the circuit with no resistor in the circuit? What if you charge a capacitor with no resistor in the circuit? If there's no resistance in the circuit, then tau equals 0, so the capacitor would charge instantaneously. The measured time using an ammeter is greater than the predicted time, since the wires and ammeter have some resistance in them in default, meaning that tau is not 0. Thank you for watching. Have a great day.